close your eyes for a moment and imagine this. You are standing in what is now known as New York, but instead of seeing the Atlantic Ocean stretching out toward the horizon, you could walk in a straight line for thousands and thousands of kilometers until you reached what would one day be Africa. There is no ocean to cross, no separated continents, just solid ground stretching beyond what your mind can comprehend. Does that seem impossible to you? Well, there was a time, not so distant in cosmic terms, when this was not only possible, but it was the reality of our planet. 300 million years ago, when the dinosaurs were still just an evolutionary dream yet to come, all the planet's dry land formed a single colossal mass that scientists call Pangea. But Pangea was not simply our current continents pushed together like puzzle pieces. It was an entirely alien world, with deserts vaster than entire countries, mountains that connected regions now separated by oceans, and a climate so extreme that seasons could last decades. Tonight, we are going to travel together through deep time to this lost world. We are going to walk through landscapes that defy our imagination, breathe a strange atmosphere, and contemplate a planet so different from ours that it could have been another world entirely. If this kind of tranquil exploration through geological time fascinates you as much as it does us here, I invite you to stay with us for this extraordinary journey. And if you find peace in these stories from deep time, consider joining us more often by subscribing, because there are so many amazing stories waiting to be told about our incredible planet. Now, prepare for a journey that will take you further back in time than your mind has ever traveled, to a world where all the geography you know must be completely reimagined. 300 million years. Try to wrap your mind around that figure for a moment. 300 million years ago, when our planet had completed only 2/3 of its history up to today, a time so remote that the entire age of the dinosaurs, from their emergence to their extinction, would fit more than 5 times in the period that separates us from that lost world. And at that point, impossibly distant in time, our planet was unrecognizable. Imagine yourself floating in space, looking down at the Earth from a distance. But this is not the Earth, you know, with its familiar continents elegantly distributed around the globe, separated by blue oceans. This Earth has all its continental mass grouped into a single hemisphere, forming a titanic island, surrounded by a ceaseless ocean. This is Pangea, and it is not just a technical name to describe joined continents. It is a word that should fill you with awe. It comes from ancient Greek, pan, which means all, and geia, which means earth. All the land, everything we know as solid ground on our modern planet, was unified into a single mass that stretched from the North Pole to the South Pole. But here is what should truly make you pause and reflect. Pangea did not form overnight. It was not as if someone had taken our current continents and pushed them together like pieces of a gigantic puzzle. No, the formation of this supercontinent was the result of a process so slow and majestic that it defies our human understanding of time. For hundreds of millions of years, continental plates the size of entire countries moved across the planet's surface at speeds that would make a fingernail's growth seem glacial. These landmasses, driven by forces so titanic that they can literally move mountains, collided with each other in a cosmic ballet of creation and destruction. Imagine those collisions. Do not think of violent, instantaneous crashes, but of encounters that lasted tens of millions of years, continents pushing against each other with such immense pressure that the Earth's crust folded like paper, creating mountain ranges that rose toward the sky as the edges of the plates fused irreversibly. When Pangea finally reached its mature form, approximately 295 million years ago, it was a landmass so vast that it is difficult to comprehend even for our modern minds. Stretching from near the North Pole to near the South Pole, It covered nearly 1/4 of the planet's surface. But the vastness of Pangea was not just a matter of size. It was a matter of scale that completely redefined what it meant to live on Earth. If you had been standing in the geographic center of this supercontinent, in what geologists call the continental interior, you would have been farther from the ocean, closer than any place on our current planet, farther from the sea than any point in the most remote deserts of Central Asia or in the heart of Australia. We are talking about thousands and thousands of kilometers of dry land in every direction as far as the eye could see. Think about that for a moment. In our modern world, you are never truly far from the ocean. Even in the most continental places, the air you breathe has been influenced by oceanic moisture. Temperatures have been moderated by the vast masses of water that surround each continent. But in the heart of Pangea, the ocean was just a theoretical idea, something that existed beyond the horizon, beyond the next horizon, and beyond the horizon after that. And this created a world with a climate so extreme, so far removed from anything we can experience today, that even the most inhospitable deserts on our planet would seem like oases by comparison. But Pangea was not only notable for its size, it was notable for its shape. It was not a perfect circle or a regular oval. It had a shape that scientists describe as similar to a gigantic sea, with a large indentation on its eastern side that formed the largest gulf our planet had ever seen, the Tethys Sea. This sea shape meant that Pangea had coastlines of impossible length. Imagine walking along the shore of this supercontinent. You could walk for years, for decades, and there would always be more coastline to explore. But it also meant that it had a continental interior of unprecedented depth, regions so far removed from any oceanic influence that they developed their own climatic rules, their own wind patterns, their own seasons, which could last what to us would be entire decades. The rest of the planet, everything that was not Pangea, was covered by a single colossal ocean called Panthalassa. Pan again meaning all, and Thalassa meaning sea. All the sea. This ocean was so vast that it contained more water than all our current oceans combined. It was a sea without significant islands, without continents to interrupt its currents, a body of water so large that storms could travel for thousands and thousands of kilometers without ever finding dry land to stop them. And here is something that should really make you reflect on the temporary nature of everything we consider permanent. Pangea was not the first supercontinent in Earth's history, nor will it be the last. Our planet has gone through multiple cycles of continental gathering and fragmentation, a process that geologists call the supercontinent cycle. Before Pangea, Rodinia existed approximately 1,000 million years ago. Before Rodinia, there were other supercontinents whose names we barely know and whose shapes we can barely imagine. And after Pangea, in the distant future, another supercontinent will form. Scientists already have names for it: Pangea Proxima or Amatia, depending on exactly how the tectonic plates move over the next 250 million years. This means that the geography we know, these continents separated by oceans, these countries with borders defined by seas and mountains, all of this is just a fleeting moment in the planet's breath. It is just a snapshot in a much longer history of gathering and separation, of creation and destruction, of worlds that form only to be eventually dismantled by the very forces that created them. But for now, let us concentrate on Pangea, because Pangea represents something unique in the history of our planet. It was the most recent supercontinent, which means we have more evidence of what it was like. We can read its history in the rocks, in the fossils, in the magnetic patterns preserved in minerals that are hundreds of millions of years old. And the story that this evidence tells us is that of a world so different from ours that it requires us to completely reimagine what it means to live on Earth. It was a world where distances were measured differently, where the climate followed different rules, where life itself had to adapt to conditions that have no parallel on our modern planet. A world where you could start a walk in what would one day be North America, and if you lived long enough and walked far enough, eventually reach what would one day be Australia, all without getting your feet wet. It was an impossible world, and it was real. While Pangea dominated one hemisphere of our planet as a titanic continental island, the rest of the Earth belonged to something equally extraordinary and vast. Panthalassa, the world-embracing ocean. Imagine for a moment the most expansive view of the ocean you have ever had. Perhaps the deck of a ship in the middle of the Pacific, where the horizon curves gently in all directions and there is no land in sight. Now multiply that feeling of immensity by 10, by 100, by 1,000. Panthalassa was larger than all our current oceans combined. The Atlantic, the Pacific, the Indian, the Arctic, and the Antarctic fused into a single mass of water that enveloped 3/4 of the planet. But Panthalassa was not simply a larger version of the oceans we know. It was something qualitatively different, a body of water so vast that it operated under its own oceanic rules, with currents that have no parallel in our modern world, and climatic patterns that defy our current understanding of oceanography. In our modern oceans, currents are constantly interrupted and redirected by land masses. The Atlantic is divided between America and Europe and Africa. The Pacific, though vast, is surrounded by the Ring of Fire. Each ocean has its limits, its continental boundaries that define how the water moves, how the heat is distributed, how storms travel. But Panthalassa had no such interruptions. It was an ocean without significant boundaries, where currents could circulate around the entire planet without encountering continental obstacles to stop them. Imagine oceanic currents that could travel for tens of thousands of kilometers in almost straight lines, transporting heat and nutrients across distances that would make the most epic migrations of our current oceans seem small. These Panthalassa supercurrents created completely unique oceanic weather patterns. Without continents to block or redirect the currents, the ocean could distribute heat much more efficiently around the planet. This meant that the temperature differences between the equator and the poles were much smaller than what we experience today. Think about the implications of this. In our current world, the poles are covered in ice because they are effectively isolated from warm oceanic currents by the configuration of the continents. But in the world of Pangea and Panthalassa, warm currents could flow much more freely toward the polar regions, maintaining the planet in a state of what climatologists call global greenhouse. During the time of Pangea, there were no permanent polar ice caps. There were no massive glaciers covering Antarctica or Greenland. The poles were temperate places with forests growing where today we find perpetual ice. It was a planet without ice seasons, where water never froze, except perhaps on the highest mountains, and where the sea level was much higher than in our modern world. But the absence of continental barriers in Panthalassa did not only affect oceanic currents, it also created the most epic storms our planet had ever seen. Imagine a hurricane forming in the middle of Panthalassa. In our modern oceans, such storms eventually find dry land that weakens or disintegrates them. But in Panthalassa, a storm could travel for thousands and thousands of kilometers of open ocean, continuously feeding on the energy of the warm water, growing in intensity until it reached scales that would make even the most devastating storms of our time seem mild. These Panthalassa superstorms could maintain their strength for weeks or even months, traveling intercontinental distances before finally reaching the coasts of Pangea. And when they reached land, They did so with a force accumulated over thousands of kilometers of unobstructed ocean. The coasts of Pangea, facing Panthalassa, experienced hurricanes of an intensity that has no precedent in our modern world, storms that could literally remodel the coastal geography, that could penetrate hundreds of kilometers inland, before finally losing their strength, carrying oceanic moisture into the continental interior in ways that helped slightly moderate the extreme climate of the heart of Pangea. But Panthalassa was not uniform in its depth or its characteristics. Like our modern oceans, it had oceanic ridges where new crust was created and abyssal trenches where old crust was recycled back into the planet's mantle. But the scale of these features was proportionally epic. The oceanic ridges of Panthalassa stretched for tens of thousands of kilometers, creating underwater mountain ranges longer than any terrestrial mountain range. These ridges were like scars on the ocean floor, marking the places where the planet literally split open to create new oceanic crust, constantly expanding the ocean and slowly pushing Pangea across the planet's surface. And the oceanic trenches of Panthalassa were abysses of unimaginable depth, places where the oceanic crust sank back into the planet's interior in a process so slow that it took millions of years, but so powerful that it would eventually recycle the entire ocean floor. These features of the ocean floor were not just geological curiosities, they were the engines that drove the entire Panthalassa system. The oceanic ridges continuously pushed new material upward from the mantle, expanding the ocean and exerting constant pressure on Pangea. The oceanic trenches provided places where this expansion could be accommodated, where old material could be recycled. It was a system in dynamic equilibrium, but an equilibrium that was destined to change, because the very forces that had created Pangea, the very mantle currents that fed the oceanic ridges of Panthalassa, would eventually work to fragment the supercontinent. But before we get to that story of destruction, we need to fully appreciate the magnificence of Panthalassa at its peak. It was more than an ocean. It was a planetary oceanic system that redefined what it meant to have water on a planet. In our modern world, we think of oceans as separate bodies of water with different names, different characteristics, different ecosystems. But Panthalassa was truly a world ocean, a singular, continuous mass of water that completely surrounded the planet's only continental mass. And in the depths of this world ocean lived marine ecosystems of a diversity and a scale that would never exist again. Without the continental barriers that characterize our modern oceans, marine life in Panthalassa could migrate freely around the entire planet. Species could evolve and disperse throughout the entire world ocean without encountering significant geographical barriers. Imagine ancestral whales that could swim around the entire planet, following uninterrupted oceanic currents. Imagine schools of fish that migrated across distances that would make the most epic migrations of our current oceans seem trivial. Imagine marine ecosystems that stretched for tens of thousands of kilometers, connected by oceanic currents that never encountered continental obstacles. It was an ocean that functioned as a single planetary system, where climatic events on one side of the world could influence the climate on the opposite side through oceanic currents that enveloped the entire globe. It was an ocean that operated on scales of time and space that defy our modern understanding of how oceanic systems work. And perhaps the most astonishing thing of all is that this world ocean, this Panthalassa that contained more water than all our combined oceans, was only the backdrop for the true protagonist of our story, the supercontinent Pangea, and the impossible landscapes it contained within. Because while Panthalassa embraced 3/4 of the planet with its aquatic immensity, Pangea dominated the remaining 1/4 with a geography so extreme, so far removed from anything we can imagine in our modern world that it requires us to completely redefine what we think we know about terrestrial landscapes. Now comes the moment to do something that may be difficult for our modern minds, to imagine landscapes that have no parallel in our current world. Landscapes so vast, so extreme, so completely removed from any contemporary geographical experience that they defy our visualization capacity. Imagine standing on the western edge of Pangea, looking east. Before you stretches not a country, not a region, but an entire continent of dry land. And beyond that continent, another continent. And beyond that, yet another. All connected, all forming a mass of uninterrupted land that stretches toward the horizon and beyond the horizon, beyond what your mind can process as a single geographical entity. To put this into perspective, imagine starting your journey on what would one day be the western coast of North America. In our modern world, if you walked east, you would eventually reach the Atlantic Ocean after crossing the width of North America. But in Pangea, if you walked east from that same position, you would pass through what would one day be North America, then through what would one day be Europe, then through what would one day be Asia, then through what would one day be Australia, and you could continue walking until you reached what would one day be the eastern coast of Africa, all without crossing a single ocean, all on continuous dry land. That distance would represent a walk of more than 20,000 kilometers across landscapes that changed dramatically but were never interrupted by significant masses of water. It is a distance so vast that walking at a normal pace, it would take you years to complete the journey. And that is only in one direction, from west to east. From north to south, Pangea stretched from near the North Pole to near the South Pole, an almost equally impossible distance. But what truly makes these landscapes something beyond imagination is not just their scale, but their nature. Because the landscapes of Pangea were not simply larger versions of what we see today. They were qualitatively different, shaped by forces and conditions that have no equivalent in our modern world of fragmented continents. Let us start with the deserts of Pangea, because they were features that completely redefined what the term desert means. In our current world, the largest deserts are impressive, but relatively contained. The Sahara, the largest desert in the modern world, covers approximately 9 million square kilometers. It is enormous by our standards, but in the context of Pangea, the Sahara would be considered a small to medium-sized desert. The deserts of the Pangean interior were the size of entire continents in our modern world. Imagine deserts that covered areas equivalent to all of Australia or all of South America. Deserts so vast that you could travel for months in any direction and never find the end of the sand dunes and arid plains. These super deserts existed because the interior of Pangea was so far removed from any source of oceanic moisture that rain was an extraordinary event, something that might not occur for years or even decades in some regions. The air arriving from the coasts had lost all its moisture long before penetrating thousands of kilometers into the continental interior. But even more astonishing than the size of these deserts was their nature. They were not like the deserts we know today, which are surrounded by wetter regions and receive at least some occasional moisture from nearby oceans. The Pangean deserts were truly continental, completely isolated from any oceanic influence, subject to temperature and dryness extremes that have no parallel in our modern world. During the day, these continental deserts reached temperatures that would make today's hottest deserts seem cool by comparison. And during the night, without the moderation of oceanic moisture, temperatures could plummet to glacial extremes, creating daily temperature variations of 50 degrees Celsius or more. Imagine walking through one of these Pangean superdeserts. During the day, the heat would be so intense that it would distort the air, creating mirages that stretched to the horizon. The ground would be so hot that it could burn through any footwear, and at night, the cold would be so severe that you could find frost on the very rocks that had been scorching just hours before. And these deserts were not temporary features. They persisted for millions of years, accumulating layers of desert sediments of a thickness that reached kilometers. Today, geologists can read the history of these ancient deserts in red rock formations found in what was once the heart of Pangea. Layers of sandstone that tell us the story of winds that blew for millions of years across landscapes drier than anything on our current planet. But Pangea was not only deserts, it also contained mountain ranges of a scale and a history that defy our modern understanding of mountainous geography. When the continental plates collided to form Pangea, they did not do so gently. Each collision was a cataclysmic event that lasted tens of millions of years, crushing and folding the Earth's crust to create mountain ranges that rivaled or surpassed anything we see today. But the most extraordinary thing about the mountains of Pangea was not just their height or their extent, but their continuity. Imagine mountain ranges that connected regions that are now separated by entire oceans. The Appalachians of North America did not end at the Atlantic coast as they do today. They continued directly into the mountains of Scotland, then into the mountains of Scandinavia, then into the mountains of Greenland, forming a single continuous mountain range that stretched for thousands of kilometers across what are now separate continents. Imagine being able to walk along a single mountain range from what is now Georgia in the United States to what is now Norway, all on the same geological formation, all part of the same mountain-building event that lasted hundreds of millions of years. These Pangean supermountain ranges reached heights that rivaled the highest mountains of our modern world. But more impressive than their height was their extent. While our modern mountain ranges are limited by oceans and separate tectonic plates, the mountain ranges of Pangea could extend without interruption across continental distances. And between these super-mountain ranges and the super-deserts flowed rivers of a scale that also has no parallel in our modern world. Rivers that originated in the mountains of what would one day be one continent and emptied into the ocean in what would one day be a completely different continent. Imagine the longest river you know, the Amazon, the Nile, the Mississippi. Now imagine rivers that made those waterways seem like streams by comparison. Rivers that flowed for thousands of kilometers through the interior of Pangea, collecting water from watersheds the size of entire modern countries, transporting sediments across distances that defy comprehension. These Pangean super rivers created valleys and floodplains of incredible extent. Imagine floodplains that stretched for hundreds of kilometers on each side of the main river, riparian ecosystems that sustained life across continental distances. When these rivers overflowed, which happened regularly due to the extreme climatic patterns of Pangea, they could flood areas the size of entire modern countries. And then there were the coasts of Pangea, which were landscapes of a beauty and a scale that also have no modern equivalent. Due to the sea shape of Pangea, the supercontinent had coastlines of extraordinary length, but these were not coasts like the ones we know today, interrupted by bays, peninsulas, and islands. They were coastlines that stretched in almost straight lines for thousands of kilometers, creating beaches and cliffs of epic continuity. Imagine walking along a beach that stretches without interruption for the distance equivalent to walking from New York to Los Angeles, a coast where you could start your walk in what would one day be Europe and end in what would one day be Africa, all following the same continuous coastline. And in the interior of the Pangean Sea was the Tethys Sea, an oceanic gulf of epic proportions that penetrated deeply into the heart of the supercontinent. The Tethys Sea was larger than the modern Mediterranean, an arm of Panthalassa that created its own climatic system and its own unique ecosystems. The coasts of the Tethys Sea were tropical regions of incredible exuberance, because this inland sea concentrated oceanic moisture and distributed it through regions that would otherwise have been part of the continental superdeserts. Here grew tropical forests of a diversity and an extent that rivaled anything in our modern world. But perhaps the most astonishing thing about all the landscapes of Pangea was simply the sense of scale that you would have experienced standing anywhere on this supercontinent. In our modern world, we are always aware in some way that we are on a continental island surrounded by oceans. Even in the most continental places, we know that the ocean exists in some relatively nearby direction. But in the heart of Pangea, you would have been truly at the center of all the planet's dry land. The nearest ocean would have been so far away that it would not have been a practical reality, but rather a theoretical idea. You would have been standing on land that stretched toward infinity in all directions, under a sky that curved toward horizons that contained only more land, more mountains, more deserts, more rivers, all stretching beyond what any person could explore in a lifetime. It was a sense of continental scale that no human being has ever experienced, because by the time our species evolved, Pangea had already begun its slow process of fragmentation toward the world of separated continents that we know today. But these impossible landscapes did not exist in a vacuum. They were shaped by, and in turn, shaped a climatic system so extreme and so far removed from anything in our modern world that it requires us to completely reimagine what we think we know about planetary climate. If the landscapes of Pangea defied the imagination, the climate of this supercontinent was even more extraordinary. It was a climatic system that operated under rules so different from those of our modern world that it requires us to abandon everything we think we know about seasons, weather, and climatic patterns. To understand the climate of Pangea, you must first imagine what it means to be truly far from the ocean. In our current world, even the most continental places are moderated by oceanic influence. Oceans act as enormous thermal regulators, absorbing heat during the summer and releasing it during the winter, keeping temperatures within relatively manageable ranges. But in the heart of Pangea, this oceanic moderation was non-existent. The air arriving from the coasts had traveled thousands and thousands of kilometers over dry land before reaching the continental interior, losing all its moisture and all its temperature moderating capacity along the way. This created what climatologists call extreme continentality, a phenomenon where land masses develop their own internal climatic systems, completely disconnected from the stabilizing influence of the oceans. In practical terms, this meant that the seasons in the interior of Pangea did not last 3 months as we are accustomed. They lasted years, decades even. Imagine a summer that begins and simply does not end. Month after month of intense heat that accumulates without the moderation of the oceanic breeze or the humid storms that could bring relief. The ground heated up like a gigantic furnace, absorbing solar radiation for months without interruption, until the terrestrial surface reached temperatures that would make vast regions of the supercontinent uninhabitable. These Pangean supersummers could last entire decades. Imagine being born during one of these extended summers and growing to adulthood without ever having experienced what we would call winter. Entire generations of plants and animals lived and died, knowing nothing but this relentless heat. And then, when winter finally arrived, it came with a vengeance that compensated for all those years of accumulated heat. The winters in the interior of Pangea were events so extreme that they redefined what continental cold means. Without nearby oceans to moderate temperatures, the supercontinent's interior turned into a continental freezer, where temperatures could drop to extremes that rivaled the most severe conditions of modern Antarctica. But the most extraordinary thing about these superwinters was not just their intensity, but their duration. Like the summers, these winters could persist for years or decades. Imagine winters that began when you were a child and did not end until you were an adult. Winters so long that entire ecosystems had to develop survival strategies that have no parallel in our modern world. And between these seasonal extremes, Pangea experienced climatic transitions that were cataclysmic events in themselves. When a supersummer finally yielded to a superwinter, the transition was not gradual as we are accustomed to in our modern world. It was abrupt and violent, with temperature changes of tens of degrees occurring in geologically instantaneous periods of time. These seasonal transitions created storms of an intensity that has no precedent in our current world. Imagine storms that fed on the temperature differences between the masses of hot air that had accumulated during decades of supersummer and the masses of cold air arriving to initiate the superwinter. These transition storms were atmospheric events so powerful that they could literally remodel the geography, creating new canyons, moving entire dunes, redistributing sediments across continental distances. But the most fascinating aspect of the Pangean climate was how the different types of climate interacted across the supercontinent's vast distances. Because Pangea stretched from near the North Pole to near the South Pole, the supercontinent simultaneously experienced all possible types of climate. While the far north was submerged in an Arctic superwinter, the center could be experiencing extreme desert conditions, and the far south could be in the midst of a tropical supersummer. This climatic distribution created temperature gradients across the supercontinent that generated wind systems of unprecedented scale. Imagine winds that originated in the polar regions of Pangea and traveled thousands of kilometers across the supercontinent without encountering oceanic obstacles to interrupt or moderate them. These Pangean superwinds could reach speeds that would make even the most powerful hurricanes of our modern world seem mild, because they fed on temperature differences that accumulated across continental distances. And when these winds finally encountered the mountain ranges of Pangea, they created orographic effects of extraordinary intensity. Imagine continental winds colliding with mountain ranges that stretched for thousands of kilometers. Air forced upward by these supermountains created clouds that reached extreme altitudes in the atmosphere, generating precipitation that could be torrential or negligible, depending on the amount of moisture the air had managed to retain during its epic journey through the continental interior. This led to one of the most extraordinary climatic phenomena of Pangea, the continental monsoons. In our modern world, monsoons are seasonal climatic systems that affect regions like South Asia, bringing intense rainfall during certain months of the year. But the Pangean monsoons operated on time and spatial scales that defy comprehension. When atmospheric conditions finally aligned to bring moisture from the coasts toward the continental interior, they did so in monsoonal events that could last months or even years. Imagine rains that began and simply did not stop for entire seasons. Precipitation so intense and prolonged that it could fill temporary lakes the size of modern seas in the depressions of the continental interior. These supermonsoons temporarily transformed entire landscapes. Deserts that had remained arid for decades suddenly became lush grasslands. Dry rivers turned into torrents that transported sediments across continental distances. Lakes that had been only dusty depressions filled up to become inland seas. And then, when conditions changed, these temporarily humid landscapes dried up again, often just as abruptly. The lakes evaporated, leaving behind salt and sediment deposits that told the story of these epic climatic transformations. The rivers were reduced to streams and then disappeared completely, leaving only their dry beds as evidence of their temporary existence. But perhaps the most astonishing aspect of the Pangean climate was how these extreme patterns self-reinforced across geological time scales. Supersummers not only heated the supercontinent's surface, they also affected air currents in the upper atmosphere, creating atmospheric pressure patterns that tended to perpetuate the conditions that had created them. Superwinters did the same, establishing high-pressure systems that blocked climatic patterns that might bring moderation. This meant that once Pangea entered an extreme climatic pattern, it tended to remain in that pattern for extraordinarily long periods. Summers extended because atmospheric conditions favored the continuation of summer. Winters persisted because the very forces that had initiated them worked to maintain them. It was a climatic system with a temporal inertia that has no parallel in our modern world of fragmented continents. A climate that, once established in a particular pattern, could maintain that pattern for decades or even centuries. And this extreme climate was not just a meteorological curiosity. It fundamentally shaped life on Pangea in ways that required unique evolutionary adaptations. Plants in the Pangean interior had to develop strategies to survive not only extreme seasons, but extreme seasons that lasted decades. Some developed forms of dormancy so deep that they could remain inactive during entire superwinters, emerging only when conditions changed decades later. Others developed the ability to store resources during favorable periods, to sustain life during unfavorable periods that could last generations. Animals in the Pangean interior developed migratory patterns of an epic scale, following favorable conditions across continental distances while fleeing climatic extremes that could last decades. Imagine migrations that were not seasonal journeys of hundreds of kilometers, but generational expeditions of thousands of kilometers that required multiple generations to complete. And through all this, the Pangean climate was intimately connected with the impossible landscapes it had created. Superdeserts existed because the extreme continental climate kept them dry for decades. Supermountain ranges influenced the wind patterns that determined where and when the torrential rains of the continental monsoons fell. It was an integrated system of geography and climate that operated on scales of time and space that defy our modern comprehension, creating conditions for life that were so extreme and so unique that they required forms of adaptation that would never again be necessary in the history of our planet. Because this impossible climate, like the impossible landscapes it helped shape, was the backdrop for ecosystems and life forms that were unprecedented in the history of the Earth and would never exist again once Pangea began its inevitable fragmentation toward the divided world of separated continents that we know today. In our modern world, oceans act as natural barriers that separate and define continental ecosystems. Life in North America evolves differently from life in Asia or Africa, precisely because these continental masses are separated by vast oceans that few species can cross. This geographical separation has been one of the main drivers of biodiversity on our planet, creating unique ecosystems on each continent. But in Pangea, these oceanic barriers simply did not exist. Imagine a world where an animal could start its life in what would one day be North America and, following natural migratory patterns, end up reproducing in what would one day be Australia, all without ever encountering a body of water larger than a river or an inland lake. Imagine plants whose pollen could be carried by the wind across distances that today would require crossing multiple oceans. This unprecedented continental connectivity created ecosystems of a scale and nature that have no parallel in our modern world. They were not continental ecosystems like the ones we know today, limited by oceans and defined by clear geographical boundaries. They were truly planetary ecosystems, systems of life that stretched across the entire land surface of the planet. The most immediate result of this connectivity was that species could disperse across distances that today we would consider impossible. In the modern world, when a new species evolves on one continent, it is essentially confined to that continent, unless it has extraordinary oceanic dispersal capabilities. But in Pangea, a species that evolved anywhere on the supercontinent potentially had access to the entire land surface of the planet. This meant that successful species could expand across geographical ranges of incredible vastness. Imagine a reptile species that developed useful adaptations in what would one day be South America, and that could then gradually disperse across all of Pangea, establishing populations in what would one day be Siberia, all by following continuous habitat corridors. These continental expansions did not happen overnight, of course. They took millions of years, with species gradually dispersing across the supercontinent's vast distances, adapting to new local environments, while maintaining genetic connectivity with their ancestral populations. But the end result was ecosystems where you could find related species, distributed across distances that today would span multiple continents. Modern paleontologists find evidence of this in the fossil record. Species from the time of Pangea, whose remains are now found on continents that are separated by entire oceans. A particularly fascinating example of this borderless connectivity is Lystrosaurus, an herbivorous reptile, the size of a pig, that lived during the late Permian and early Triassic periods. Fossils of Lystrosaurus have been found in what is now South Africa, Antarctica, India, China, and Russia. In our modern world, it would be impossible for a single terrestrial species to have such a wide distribution. But in Pangea, Lystrosaurus had simply found suitable habitats distributed across the entire supercontinent and had colonized each of them. But the continental connectivity of Pangea did not only allow the dispersal of individual species, it also created the possibility of migrations on a scale that defies imagination. In our modern world, the most epic migrations are impressive, but relatively limited events. The wildebeest of the Serengeti migrate hundreds of kilometers following the seasonal rains. Whales migrate thousands of kilometers between their feeding and breeding areas, but these migrations are limited by the available geography and by oceanic barriers. In Pangea, migrations could operate on complete continental scales. Imagine herds of herbivores following seasonal climatic patterns across distances that today would require crossing multiple continents. Remember that the seasons in Pangea could last decades, and that favorable climatic patterns moved gradually across the supercontinent in cycles that lasted centuries. This created the possibility of multi-generational migrations, where animal populations constantly moved across the supercontinent, following optimal climatic conditions in a ceaseless journey that could take multiple generations to complete. Individual animals were born, lived, and died as part of an epic migration that was much larger than any individual life. Imagine herds of animals whose migratory routes stretched from what would one day be the Canadian Arctic to what would one day be the Kalahari Desert, following corridors of vegetation that changed with the superclimatic cycles of Pangea. These migrations were not round trips like modern migrations, but perpetual, unidirectional movements that followed favorable conditions around the entire supercontinent. And the predators that depended on these migratory herbivores developed their own continental tracking strategies. Imagine carnivores, whose hunting territories stretched across distances that today would span multiple continents, following the migratory herds across landscapes that changed from Arctic tundra to tropical desert during the course of their lives. But perhaps the most fascinating aspect of life on Pangea was how this continental connectivity affected the evolutionary processes themselves. In our modern world, oceanic separation allows species populations to evolve independently, developing unique adaptations that can eventually lead to the formation of new species. This process, called allopatric speciation, has been responsible for much of the biodiversity we see on our current planet. But in Pangea, this type of geographical isolation was much more difficult to achieve. Populations were constantly connected by gene flow across the supercontinent's vast distances. This meant that speciation occurred differently, requiring types of isolation that did not rely on geographical barriers. The result was that Pangea had fewer total species than our modern world, but the species that did exist had geographical ranges of unprecedented vastness. It was a world with lower species diversity, but with individual species of planetary distribution. This continental connectivity also meant that important evolutionary events could have almost immediate planetary effects in geological terms. When a species developed an important evolutionary innovation anywhere on Pangea, that innovation could potentially disperse across the entire supercontinent in relatively short periods of time. This accelerated certain aspects of evolution while slowing down others, creating evolutionary patterns that have no parallel in our modern world of fragmented continents. But the connectivity of Pangea was not uniform across the entire supercontinent. The superdeserts of the continental interior acted as partial barriers, creating dispersal corridors that followed the wetter regions around the edges of the supercontinent and along the valleys of the super rivers. This created complex biogeographical patterns where some species could disperse freely across certain corridors while being excluded from other habitats by the extreme climatic conditions. The result was a continental mosaic of connected ecosystems, but also partially isolated by the extreme environmental conditions that characterized different regions of Pangea. The coastal regions of Pangea sustained relatively lush ecosystems, moderated by oceanic influence and connected by humid corridors that followed the coastlines. These coastal ecosystems were biological highways that allowed the rapid dispersal of species adapted to humid conditions. The Tethys Sea, that great gulf that penetrated the heart of Pangea, created its own system of unique ecosystems. The regions around the Tethys Sea experienced humid tropical climates that sustained forests of an exuberance that rivaled anything in our modern world. These Tethian forests were refuges of biodiversity that acted as genetic reservoirs during periods of extreme climate in other parts of the supercontinent. And the super rivers of Pangea created riparian corridors that penetrated deeply into the continental interior, carrying both water and life into regions that would otherwise have been completely arid. These river corridors sustained linear ecosystems that stretched for thousands of kilometers, creating dispersal highways that connected the humid coastal regions with the steppes and deserts of the interior. But perhaps the most extraordinary aspect of life on Pangea was simply the scale of the individual ecosystems. In our modern world, even the largest ecosystems are limited by continental boundaries. The Amazon, for example, is an impressive ecosystem, but it is contained within South America. The African savanna is vast, but it is limited to Africa. In Pangea, individual ecosystems could stretch across distances that today would span multiple continents. Imagine grasslands that stretched without interruption from what would one day be Canada to what would one day be Argentina. Imagine boreal forests that extended in a continuous band around the polar regions of Pangea, connecting what would one day be Siberia, Canada, Scandinavia, and Alaska in a single planetary forest ecosystem. These Pangean mega-ecosystems operated as integrated systems on a scale that defies comprehension. Climatic events in one part of the system could have cascade effects that propagated across the entire continent. Population fluctuations of key species could influence ecosystems at distances of thousands of kilometers. It was a world where life truly operated on a planetary scale, without the fragmentations and isolations that characterize our modern world. A world where ecological processes could unfold without interruption across the entire available land surface of the planet. But this planetary connectivity also created vulnerabilities that do not exist in our fragmented world. When conditions changed, when the climate became adverse, when catastrophic events occurred, the effects could propagate through the entire connected system of Pangea in ways that were impossible in a world of separate continents. And eventually, those vulnerabilities would be tested by events that would not only change life on Pangea, but would begin the process that would eventually fragment the supercontinent itself, creating the divided world of separate continents that we know today. In our modern world, mountains are natural barriers that separate regions and define borders. The Andes separate the coast from the interior of South America. The Himalayas divide the Indian subcontinent from the rest of Asia. The Alps create a natural border between the north and south of Europe. Mountains fragment, separate, isolate. But in Pangea, mountains did exactly the opposite. They united worlds that are now separated by entire oceans. To truly understand the magnitude of what this means, you need to completely reimagine your concept of what a mountain range can be. In our fragmented world, even the longest mountain ranges eventually reach oceanic coasts, where they simply end. The Andes stretch for the length of South America, but they eventually reach the ocean and cannot continue. The Himalayas stretch across Asia, but they are limited by the borders of the Asian continent. In Pangea, mountain ranges maintained no such limitations. They could truly extend from pole to pole, crossing what are now multiple continents in continuous mountain ranges that narrated the epic story of continental collisions that lasted hundreds of millions of years. The most extraordinary mountain range of Pangea was what geologists now call the Appalachian-Caledonian-Variscan mountain system. But these technical names do not capture the magnificence of what it truly was: a single continuous mountain range that stretched from what is now the southeastern United States, across what is now the North Atlantic, to what are now the British Isles, Scandinavia, and the mountains of Central Europe. Imagine being able to start a mountain hike in the mountains of Georgia, in the southeastern United States, and continue walking along the same geological formation, the same continuous mountain range, until you reached the mountains of Norway. You would not be crossing oceans. You would not be jumping between separate mountain ranges. You would be following a single supermountain range that connected what we now consider completely separate continents. But understanding these mountains requires understanding how they formed, because their history is also the story of how Pangea itself was assembled. The mountains of Pangea did not form in the gradual and relatively gentle manner that we might imagine. They formed through continental collisions that were events so cataclysmic and prolonged that they literally redefined the surface of the planet. Imagine two continental masses the size of North America, moving toward each other across the ocean for tens of millions of years, driven by tectonic forces so powerful that they could move entire continents. Now, imagine the moment of collision, not an instantaneous crash, but an encounter that lasted millions of years, as the edges of the continents wrinkled, folded, and rose toward the sky. During these supercollisions, the Earth's crust at the edges of the continents had nowhere to go except up. Layers of rock that had been at the bottom of ancient oceans were pushed to altitudes of several kilometers. Mountains that had taken millions of years to form were folded like paper and stacked one on top of the other. The result was mountain ranges of a height and extent that rivaled or surpassed anything in our modern world. But more impressive than their height was their continuity. While our modern mountains are limited by individual tectonic plates, the mountains of Pangea were formed by the fusion of multiple supercontinental plates, creating mountain ranges that could stretch without interruption across distances that today would require crossing entire oceans. These Pangean supermountain ranges reached altitudes that likely rivaled the modern Mount Everest, but they extended for thousands of kilometers without interruption. Imagine the Himalayas, but instead of being confined to the edge of the Indian subcontinent, extending continuously from the Arctic to Antarctica. But the mountains of Pangea were not just impressive in their scale. They were also fascinating for the stories they told about the supercontinent's formation. Each mountain range in Pangea marked a suture zone where two ancient continental masses had fused. Modern geologists can read these collision stories in the rocks, identifying the chemical and structural signatures that reveal when and how the different pieces of Pangea came together. The Appalachians, for example, formed when what is now North America collided with what is now Africa, approximately 320 million years ago. But this collision was not an isolated event. It was part of a series of collisions that also created the mountains we now see in Scotland, Ireland, Norway, and other parts of Europe. The reason we can find almost identical rocks in the Appalachians of the United States and in the mountains of Scotland is not coincidence. It is because they were literally part of the same mountain range, formed by the same continental collision, separated only later, when the Atlantic Ocean began to open during the fragmentation of Pangea. Imagine the implications of this. It means you could pick up a rock in the mountains of New Hampshire and find a nearly identical rock in the Scottish Highlands, because those rocks formed as part of the same mountain-building process in the same super-mountain range 300 million years ago. This geological continuity extends far beyond the rocks. Geologists have found fossils of identical plants and animals on what are now opposite sides of the Atlantic Ocean, preserved in rock layers that formed when those regions were part of the same continental mountain range. But perhaps the most astonishing thing about the mountains of Pangea was how they influenced the supercontinent's climate and ecosystems. These supermountain ranges acted as continental climate regulators, creating rain shadows of an epic scale and directing wind patterns across distances that spanned the entire supercontinent. When Pangea's continental winds encountered these supermountain ranges, they were forced upward to extreme altitudes, where they cooled and released any moisture they might have retained during their epic journeys through the continental interior. This created orographic effects of unprecedented intensity. On the windward side of these mountains, where the winds ascended, precipitation could be torrential, creating regions of lush vegetation, even in the context of Pangea's extreme continental climate. But on the leeward side, the mountains created rain shadows that stretched for hundreds of kilometers, contributing to the formation of the superdeserts that characterized much of the Pangean interior. These supermountain ranges also acted as dispersal corridors for species that could tolerate high-altitude conditions. The mountains of Pangea created elevated highways that connected similar climatic regions across continental distances, allowing cold-adapted species to disperse from the polar regions to the tropical mountains without having to traverse the hot deserts of the lowlands. Imagine mountainous ecosystems that stretched in continuous chains from the Arctic to the tropics, creating high-altitude biodiversity corridors that connected regions that would otherwise have been completely isolated by the extreme climatic conditions of the lowlands. And within these supermountain ranges, the topography created microclimates of extraordinary diversity. The mountains of Pangea included deep valleys that were protected from the extreme continental winds, creating climatic refugia, where life could persist during the most severe periods of Pangea's superclimatic cycles. These mountain valleys acted as natural greenhouses, trapping moisture and moderating temperatures in ways that created oases of relatively mild conditions in the context of the extreme continental climate. During the superwinters, which could last decades, these protected valleys could maintain temperate ecosystems that served as refuges for species that otherwise would not have been able to survive the supercontinent's climatic extremes. But the mountains of Pangea were also dynamic, constantly changing as the tectonic forces that had created them continued to operate. Even after the main continental collisions had ended and Pangea had reached its mature configuration, the supermountain ranges continued to rise and erode in cycles that lasted millions of years. The same forces that had pushed these mountains upward remained active, but now worked against the forces of erosion that constantly wore down the highest peaks. This continuous battle between tectonic uplift and erosion created mountainous landscapes of extraordinary complexity and beauty. Imagine canyons that cut through entire mountain ranges, created by super rivers that had the power to maintain their courses even as the mountains rose around them. Imagine U-shaped valleys carved by glaciers that formed on the highest peaks and flowed down the mountain slopes. And as the mountains eroded, the resulting sediments were transported by the super rivers of Pangea to the lowlands, where they accumulated in deposits that reached thicknesses of kilometers. These mountainous sediments contained minerals and nutrients that fertilized the floodplains, creating some of the most fertile regions of the supercontinent. But perhaps the most extraordinary thing about the mountains of Pangea was simply the sense of continuity they would have provided to any hypothetical traveler. In our modern world, when you travel from one mountain range to another, you have to cross oceans, plains, deserts. The mountains are fragmented, separated, isolated. But in Pangea you could have followed continuous mountain ranges across distances that today would require traveling between multiple continents. Imagine starting in the snowy peaks of what would one day be Scandinavia and being able to walk through continuous mountains until you reached the tropical peaks of what would one day be West Africa, all following the same super mountain range, all part of the same integrated mountain system. It was an experience of geographical continuity that no human being has ever had, because by the time our species evolved, these super mountain ranges had already been fragmented by the opening of the oceans that separate our modern continents. But the mountains that united worlds were not simply static features of the Pangean landscape. They were also the geological records of the processes that would eventually begin to fragment the supercontinent, because the same tectonic forces that had created Pangea were already working to dismantle it. In the depths beneath these supermountain ranges, new convection currents in the Earth's mantle began to develop, currents that would eventually create the forces that would open cracks in the heart of Pangea and begin the process of fragmentation that would create our modern world of separate continents. While the mountains of Pangea told the story of how the supercontinent had been assembled, the depths beneath its surface harbored forces that would eventually narrate a very different story, the story of its destruction. Because beneath the apparently solid crust of Pangea, the Earth's mantle was undergoing changes that would create some of the most catastrophic volcanic events in our planet's history. To understand what was happening beneath Pangea, you need to imagine the Earth's interior as a dynamic system of convection currents that operates on geological timescales. The mantle, that layer of hot rock that exists between the crust and the core, is in constant motion with currents that rise and fall in cycles that last hundreds of millions of years. When all the planet's continents came together to form Pangea, they created something equivalent to a gigantic insulating blanket that covered a significant portion of the land surface. This continental blanket trapped the heat that would normally be dispersed more uniformly across the planet's surface. Imagine what happens when you cover a pot of boiling water with a lid. Heat accumulates beneath the lid until it finally finds a way to escape, often violently. Something similar was happening beneath Pangea, but on scales of time and energy that defy human comprehension. For tens of millions of years after Pangea reached its mature configuration, heat accumulated beneath the supercontinent in a gradual, inexorable manner. Convection currents in the mantle began to change, organizing into patterns that concentrated more and more thermal energy directly beneath the unified continental mass. The eventual result of this heat accumulation was the formation of what geologists call mantle superplumes, massive columns of molten rock that ascended from the depths of the mantle toward the surface, loaded with energies that rivaled the power of thousands of modern volcanoes combined. When these superplumes finally reached the surface, they created volcanic events of a magnitude that has no precedent in human experience. The most famous and devastating of these events were the Siberian Traps, a volcanic eruption that occurred approximately 252 million years ago and fundamentally changed the history of life on Earth. But calling the Siberian Traps a volcanic eruption is like calling the Pacific Ocean a puddle of water. The numbers involved defy comprehension. Approximately 4 million square kilometers of basaltic lava, enough to cover the entire European Union, with a layer of molten rock several kilometers thick. Imagine volcanoes that were not conical mountains like Vesuvius or Mount Fuji, but fissures in the Earth's crust that stretched for hundreds of kilometers, spewing lava at rates that would have filled the Grand Canyon in a matter of days. Imagine eruptions that did not last weeks or months, but continued for hundreds of thousands of years, creating lava flows that spread over continental distances. The Siberian Traps were not just a manifestation of geological violence, they were a fundamental reorganization of the planet's surface. During the peak of volcanic activity, these eruptions released amounts of carbon dioxide, sulfur dioxide, and other gases into the atmosphere that dramatically altered the Earth's atmospheric chemistry. But the gases were only the beginning of the atmospheric impact. The eruptions also released volcanic ash in such massive quantities that they significantly blocked sunlight, creating what scientists call volcanic winter on scales that lasted decades. Imagine skies that remain darkened by volcanic ash for consecutive years, reducing photosynthesis to levels that could not sustain terrestrial ecosystems. Imagine global temperatures that wildly fluctuated between the extreme warming caused by greenhouse gases and the extreme cooling caused by the sun-blocking ash. These atmospheric changes triggered the most severe mass extinction in the history of terrestrial life, the Permian-Triassic extinction, also known as the Great Dying. Approximately 96% of marine species and 70% of terrestrial species became extinct during this event, fundamentally redefining the trajectory of evolution on our planet. But the Siberian Traps were not the only massive volcanic event associated with Pangea. As the mantle superplumes continued to develop beneath the supercontinent, they created a series of volcanic provinces that stretched across different regions of Pangea during periods of time that spanned tens of millions of years. The Central Atlantic Magmatic Province, CAMP, which formed approximately 200 million years ago, created basaltic lava flows that extended from what is now eastern North America to what is now West Africa. Imagine volcanic eruptions so massive that their products can now be found on opposite sides of the Atlantic Ocean, evidence that these eruptions occurred when those regions were still connected as part of Pangea. These volcanic events were not just spectacles of destruction, they were also the surface manifestations of the deep processes that would eventually fragment Pangea. The superplumes that fueled these massive eruptions were also creating the forces that would begin to crack the supercontinent from within. Imagine the heat and pressure of these superplumes pushing upward against the Pangean crust from below, creating stresses that gradually began to fracture the supercontinent's seemingly solid surface. What began as volcanic activity eventually evolved into continental rifting, the process that would open the first cracks in Pangea and initiate its fragmentation into the separate continents we know today. But before those cracks fully opened, Pangea's volcanic activity created landscapes of a beauty and a terror that have no parallel in our modern world. Imagine lava fields that stretched to the horizon in all directions, rivers of molten rock that flowed for hundreds of kilometers from their volcanic sources until finally solidifying into basaltic plains that covered areas the size of entire modern countries. These volcanic landscapes were not sterile. Over time, as volcanic activity subsided and the lava flows cooled, they became some of the most fertile soils of the supercontinent. The volcanic rocks, rich in minerals, gradually decomposed to create soils that could support lush vegetation once climatic conditions stabilized. But the stabilization process took millions of years, during which vast regions of Pangea were dominated by active volcanic landscapes that constantly redefined the local geography. Imagine lava lakes that remained molten for decades, creating bodies of liquid rock the size of modern lakes. Imagine geysers of volcanic gases erupting from fissures in the crust, creating columns of steam and gases that rose for kilometers into the atmosphere. Imagine hot springs that created oases of geothermal heat in regions that otherwise experienced the extreme superwinters of Pangea's continental climate. These volcanic phenomena also created their own unique microclimates. Water vapor emissions from hot springs and geysers could create local pockets of moisture that sustained specialized vegetation, even in the context of the continental superdeserts. Volcanic gas emanations could create local atmospheres with unique chemical compositions that favored certain types of life over others. And during periods of most intense volcanic activity, these landscapes became spectacles of a grandeur that defies description. Imagine horizons illuminated by the glow of dozens of active volcanoes simultaneously, skies painted red and orange by suspended volcanic ash, and the constant rumble of the Earth itself, remodeling through forces that operated on scales that made any modern volcanic activity seem insignificant. But perhaps the most astonishing thing about Pangea's volcanic activity was how it was intimately connected with the processes that would eventually transform the supercontinent into our modern world of fragmented continents. The same superplumes that created these massive volcanic eruptions were also reorganizing the convection currents in the deep mantle. These new convection currents began to exert tensional forces on the Pangean crust, forces that would eventually overcome the supercontinent's structural resistance. In the regions where these tensional forces were most intense, the continental crust began to stretch and thin. The first manifestations of this process were rift valleys, long, narrow depressions, where the crust was literally being pulled apart under the influence of deep mantle forces. These rift valleys were initially filled with lakes and later with shallow seas, as the crust continued to stretch and the sea level penetrated the depressions. But these bodies of water were only the prelude to something much more dramatic, the formation of completely new oceans that would eventually separate Pangea into the fragmented continents we know today. The volcanic landscapes of Pangea were both the climax of the supercontinent and the beginning of its end. They were the manifestation of internal forces that had reached such intensity that they not only remodeled the planet's surface, but began to reorganize the fundamental structure of the Earth's crust. And as these forces continued to intensify, the days of Pangea as a unified supercontinent were numbered. The first cracks were already beginning to appear in the seemingly solid surface of the supercontinent. Cracks that would eventually widen into oceans and forever transform the geography of our planet. After more than 50 million years as a unified continental mass, Pangea had reached a kind of dynamic equilibrium. Its superdeserts stretched for continental distances. Its supermountain ranges connected regions that are now separated by oceans, and its ecosystems operated on planetary scales. To any hypothetical observer, the supercontinent might have seemed like a permanent feature of our planet, something as fundamental and enduring as the mountains or the oceans. But beneath this apparent stability, the same forces that had assembled Pangea were already working to dismantle it. The process began so subtly that it would have been imperceptible to any surface observer. In scattered regions across the supercontinent, the Earth's crust began to experience stresses that manifested as small fractures, barely perceptible cracks appearing in rock formations that had remained solid for millions of years. These first cracks were not dramatic events. There were no massive volcanic eruptions to announce them. There were no catastrophic earthquakes to mark their appearance. They were simply lines of weakness that gradually developed as deep convection currents in the Earth's mantle slowly reorganized the forces acting on the continental crust. But for modern geologists who can read the history and the rocks, these seemingly insignificant cracks mark one of the most important moments in our planet's history, the beginning of the end of Pangea. To understand why these cracks were so significant, you need to comprehend the extraordinary forces required to fracture a supercontinent. Pangea was not simply a landmass that had been superficially pushed together. It was a deeply integrated continental structure with roots that extended tens of kilometers into the upper mantle, welded together by hundreds of millions of years of tectonic pressure and fusion. Fracturing this structure required forces that operated on scales that defy human comprehension. The responsible convection currents had to reorganize flows of molten rock, moving across thousands of kilometers in the deep mantle, generating pressures that would eventually overcome the structural resistance of an entire continental mass. The process began with what geologists call thermal doming, the gradual uplift of regions of the crust as mantle superplumes pushed upward from below. Imagine the Pangean crust being slowly arched upward by columns of hot rock ascending from depths of hundreds of kilometers, creating gentle elevations that rose at rates of centimeters per century. These thermal uplifts were so gradual that they would have been imperceptible during any individual human lifespan, but over millions of years they created mechanical stresses that began to stretch and thin the continental crust from within. As the crust stretched, the first rift valleys began to form, linear depressions, where the land surface was literally being pulled apart under the influence of tensional forces. These rifts did not open uniformly or predictably. They appeared where the crust was naturally weakest, following ancient fracture lines or zones where different geological terrains had fused imperfectly during the assembly of Pangea. One of the first and most significant of these rift systems began to develop in what is now the region between North America and Africa. Approximately 230 million years ago, a line of weakness began to form along what would eventually become the eastern coast of North America and the western coast of Africa. Initially, this rift was no more than a shallow valley, a linear depression that stretched for hundreds of kilometers through the interior of Pangea. For millions of years, this valley gradually deepened as tensional forces continued to stretch the crust, but there was still no oceanic water involved. It was simply a scar on the supercontinent's surface, a mark indicating where internal forces were beginning to overcome the continental mass's structural resistance. But as the rift continued to develop, it reached a point of no geological return. When the stretching of the crust reached a certain critical threshold, the rifting process accelerated dramatically. What had been a gradual thinning over millions of years turned into active fracturing that occurred on timescales that were rapid by geological standards. Imagine the moment when the continental crust finally yielded completely. It was not an instantaneous event like the breaking of a rope, but a process that lasted hundreds of thousands of years. As the fractured crust allowed the molten mantle to ascend from below, creating new oceanic crust in the space that had opened between the separated continental masses. This was the birth of the Atlantic Ocean, but not as we know it today. Initially, it was barely a narrow sea, a body of water that resembled the modern Red Sea more than the vast ocean it would eventually become. But this narrow sea represented a fundamental transformation. For the first time in more than 50 million years, Pangea was no longer a unified supercontinent. The process of separation, once initiated, was self-perpetuating. As new oceanic crust formed in the center of the expanding rift, the forces that had initiated the separation intensified. Convection currents in the mantle reorganized to accommodate the new flow pattern, creating oceanic ridges that actively pushed the separated continental masses further and further apart. But Pangea's fragmentation did not occur uniformly or simultaneously across the entire supercontinent. Different regions began to separate at different times, following lines of weakness that had been established by the unique tectonic history of each region. While the Proto-Atlantic opened between North America and Africa, other rift systems began to develop in different parts of Pangea. The Indian Ocean began to form as what is now India, separated from what is now Antarctica. The Tethys Sea, which had been a gulf penetrating Pangea, began to expand as the continental masses on both sides moved in opposite directions. Each of these separations followed the same basic pattern: initial thermal doming, continental rift formation, final crust fracturing, and oceanic invasion. But each also had its own unique characteristics, determined by the local geology and the specific configuration of mantle currents in each region. The most extraordinary thing about this fragmentation process was its irreversibility. Once the first narrow oceans had formed between the separated continental masses, there were no forces that could bring those continental masses back together. Convection currents feeding the new oceanic ridges ensured that the separation continued indefinitely, with the continents moving further and further away from each other at rates that would eventually reach several centimeters per year. But during the initial stages of fragmentation, the changes would have been subtle from the perspective of any surface observer. The new oceans were narrow, more like inland seas than the vast expanses of water they would eventually become. The separated continental masses were still close enough that species migration between them would have been possible, although increasingly difficult. Gradually, however, these narrow seas widened into true oceanic barriers that began to isolate the continental ecosystems that had been connected during the time of Pangea. Species that could once migrate freely across the entire supercontinent suddenly found themselves confined to individual continental masses, initiating allopatric speciation processes that would eventually create the regionalized biodiversity that characterizes our modern world. Pangea's planetary ecosystems began to fragment along with the physical geography. The mega-ecosystems that had stretched across continental distances were divided into separate ecosystems that began to evolve independently. The supermigrations that had characterized life on Pangea became impossible as oceanic barriers interrupted the continental routes. And as the oceans continued to widen, the extreme continental climates that had characterized Pangea began to moderate. The new oceans brought maritime influences that softened the supercontinent's seasonal supercycles. The interior superdeserts began to receive oceanic moisture that gradually transformed them into more habitable environments. But perhaps the most significant thing about the initial fragmentation of Pangea was that it marked the beginning of the geographical configuration that would eventually produce our modern world. The fracture lines that developed during this era determined where the oceans and continents of our current planet would be. The forces that initiated the separation 200 million years ago are still active today, continuing the process that will eventually lead to the formation of the next supercontinent in the distant future. The first cracks in Pangea were not simply the end of a geological era, they were the beginning of the geological era that we still inhabit, the beginning of the fragmented world of separate continents that defines modern geography. It was the moment when our planet began its transformation from a unified world to the diverse and regionally distinct world we know today. And once those first cracks had fully opened, there was no stopping the process that would eventually transform Pangea from a unified supercontinent into the separate continents we know today in a geological ballet of fragmentation that would continue for the next 200 million years. Once the first cracks had opened in Pangea, the supercontinent entered a phase of transformation that fundamentally redefined the nature of our planet. But this transformation was not a sudden or dramatic collapse. It was a process of extraordinary geological elegance, a cosmic ballet executed in super slow motion that took 200 million years to complete and is still ongoing today. To truly appreciate the magnificence of this process, you need to reimagine your concept of time. The events we are going to explore occurred at speeds that are imperceptible during any individual human lifetime, but which are extraordinarily fast by geological standards. The continents separated from each other at speeds similar to the growth of human fingernails, barely a few centimeters per year, but fast enough to completely transform planetary geography over the course of tens of millions of years. Imagine witnessing this ballet from a cosmic perspective, with the ability to accelerate time until millions of years passed as minutes. You would see Pangea's continental masses gradually separating like gigantic ice flows, rotating and sliding across the planet's surface, on trajectories determined by forces operating in the depths of the Earth's mantle. The fragmentation process followed patterns that revealed the underlying mathematical elegance of planetary tectonic systems. It was not random or chaotic. It was a highly organized process, directed by the laws of physics that govern convection flow in the mantle and fracture mechanics in the Earth's crust. The first act of this cosmic ballet was the separation between North America and Africa, which had begun with the first cracks approximately 230 million years ago. But this separation did not occur as a simple and direct fracture. It followed a complex pattern of rift propagation that reflected the structural weaknesses inherited from Pangea's original formation. Imagine the nascent Atlantic Ocean as a geological zipper that gradually opened from south to north. The separation began in what is now the region between Brazil and West Africa, where mantle currents had created the first zones of significant weakness. From this initial point, the fracture propagated northward and southward at speeds of a few centimeters per year. But this propagation was not uniform. In some regions, the crust yielded relatively easily, allowing the ocean to widen quickly. In other areas, particularly resistant rock formations slowed the process, creating temporary bottlenecks where continental masses remained connected by land bridges even after the surrounding regions had completely separated. These continental land bridges acted as the last corridors of biological connectivity between the separating continental masses. For millions of years, while the Atlantic Ocean widened to the north and south, these remaining land connections allowed species to continue migrating between what would eventually become completely separate continents. Gradually, however, even these last bridges succumbed to the rifting forces. the moment when the last land connection between North America and Africa finally broke, approximately 180 million years ago, marked a point of no return in the history of terrestrial life. For the first time in hundreds of millions of years, the planet's terrestrial ecosystems were truly fragmented by oceanic barriers that could not be crossed by most species. But even as the Atlantic Ocean widened between North America and Africa, other acts of this continental ballet unfolded simultaneously in different regions of the fragmented supercontinent. To the south, what we now know as South America began its own separation from Africa, following a similar pattern, but temporally displaced. This separation began approximately 140 million years ago, creating the South Atlantic extension of the rifting system that had begun further north. Simultaneously, on the opposite side of what remained of Pangea, the Indian subcontinent began its epic journey from its original position against Antarctica toward its final destination against Asia. This journey represented one of the most dramatic continental migrations in Earth's history. A continental mass the size of modern India, traveling across thousands of kilometers of newly formed ocean at speeds that reached more than 15 centimeters per year, extraordinarily rapid by tectonic standards. India's journey was facilitated by the formation of a particularly active oceanic ridge that pushed the subcontinent northward as if it were being transported by a geological conveyor belt. For more than 100 million years, India sailed across the forming Indian Ocean, carrying with it unique ecosystems that had evolved during its continental isolation. When India finally collided with Asia, approximately 50 million years ago, the impact created the highest mountains in the modern world, the Himalayas. But this collision was not an instantaneous event. It was a process of continental compression that lasted tens of millions of years, gradually pushing the crust upward to create peaks that rivaled or surpassed anything that had existed during the time of Pangea. Meanwhile, other continental masses executed their own tectonic choreographies. Australia separated from Antarctica and began its drift northward. Africa gradually rotated counterclockwise as it separated from both South America and Antarctica. Madagascar broke away from the east coast of Africa and assumed its isolated position in the western Indian Ocean. Each of these separations followed unique dynamics determined by the specific configuration of mantle currents in each region. Some separations were relatively smooth, with the continental masses sliding apart from each other along clearly defined continental margins. Others involved complex fractures that divided individual continental masses into multiple fragments. The separation between North America and Europe, for example, involved the formation of multiple rift arms that created a complex oceanic configuration in the North Atlantic. Greenland separated from both North America and Europe, but at different times and speeds, creating a pattern of oceanic opening that reflects the interaction between multiple, simultaneously active rifting systems. The most extraordinary thing about this continental ballet was how each individual movement was coordinated with all the other movements to create a coherent planetary system. The continents did not move independently. Their movements were coupled by the global mantle convection currents, which operated as an integrated system. When India accelerated northward, for example, this movement influenced the convection patterns that affected the movements of other continents. When the Atlantic widened, it created changes in the forces acting on the Pacific. Everything was connected in a planetary dance, where each individual step contributed to the overall choreographic pattern. And as the continents separated, the oceans that formed between them developed their own complex internal dynamics. The new oceanic ridges created marine current systems that had not existed during the time of Pangea. These oceanic currents, in turn, influenced global climatic patterns in ways that affected both marine and terrestrial ecosystems. The widening of the Atlantic Ocean, for example, eventually allowed the development of the Gulf Stream, which transports tropical water northward along the east coast of North America before crossing toward Europe. This current keeps Western Europe significantly warmer than it would be based only on its latitude, demonstrating how tectonic changes can have climatic effects that persist for tens of millions of years. Similarly, the separation of Australia from Antarctica eventually allowed the development of the Antarctic circumpolar current, which now thermally isolates Antarctica from the rest of the world's oceans. This current contributed significantly to the cooling of Antarctica and the development of its current ice sheet, another example of how continental fragmentation can have profound and lasting climatic consequences. But perhaps the most astonishing aspect of this continental ballet was its apparent retrospective inevitability, combined with its prospective unpredictability. Once fragmentation began, the general patterns of the process were determined by the laws of physics and the configuration of mantle currents. But the specific details of the timing, speed, and direction of continental movements were sensitive to small variations in initial conditions that would have been impossible to predict. This is an example of what scientists call sensitive dependence on initial conditions in complex systems. Small differences in crustal properties or mantle configurations could have led to completely different fragmentation patterns, resulting in a modern world with a totally different geography. Imagine how different our world would have been if India had traveled westward instead of northward, colliding with Africa instead of Asia, or if Australia had remained connected to Antarctica, creating a southern hemisphere supercontinent. These alternative possibilities were not just speculations. They were plausible outcomes that were excluded by the specific details of how mantle currents unfolded during Pangea's fragmentation. And as this continental ballet continued over tens of millions of years, it gradually created the geographical configuration that defines our modern world. Oceans widened to their current dimensions. Continents assumed their familiar positions. Climatic patterns stabilized into configurations that have persisted for millions of years. But this ballet is not over. It continues today at the same slow but inexorable speed that has characterized the entire process. The Atlantic Ocean is still widening by a few centimeters per year. The Pacific is contracting at a similar rate. The continents continue their slow drift toward configurations that will eventually create the next supercontinent in the distant future. And so, the ballet that began with the first cracks in Pangea 200 million years ago continues to unfold, gradually transforming our planet toward a geographical future that will be as different from our current world as our current world is from the impossible world of Pangea. As you wake up this morning in the familiar world of continents separated by oceans, you might think of Pangea as simply a curiosity of the remote past, a fascinating but irrelevant chapter in our planet's ancient history. But the truth is much more extraordinary. Pangea never truly left. Its echoes reverberate through every aspect of our modern world, from the distribution of life to the chemistry of the oceans, from the climate we experience to the minerals we extract from the earth. Every fossil we find, every oceanic current that moderates our climate, every mountain range that defines our landscapes, every species that inhabits our planet, all bear the fingerprints of that impossible supercontinent that existed 300 million years ago. Let us start with something you can observe directly: the coastlines of the modern continents. If you have ever looked at a map of the Atlantic Ocean, you have probably noticed how the coasts of South America and Africa seem to fit together like puzzle pieces. This is not coincidence. It is direct evidence that these continents were once joined as part of Pangea. The east coast of Brazil and the west coast of Africa are literally the scars of the separation that began 140 million years ago. But this geographical compatibility goes far beyond simple coastal shapes. When geologists study the rocks on both sides of the Atlantic, they find identical geological formations that stretch from one continent to the other, as if someone had cut through a single geological structure with a gigantic knife. The Appalachians of North America, for example, do not truly end at the Atlantic coast, as modern maps suggest. They continue across the ocean floor and emerge in the mountains of Scotland, Ireland, and Norway. These apparently separate mountain ranges are actually fragments of the same supermountain range that formed during the assembly of Pangea, later divided by the opening of the Atlantic Ocean. You can go to New Hampshire and pick up a rock, then travel to the Scottish Highlands and find practically identical rocks with the same age, the same mineral composition, and the same chemical signatures. These rocks formed as part of the same mountain-building event in the same supermountain range, when those regions were joined in Pangea 300 million years ago. But the echoes of Pangea extend far beyond geology. They are written in the book of life itself. When Charles Darwin formulated his theory of evolution, one of the problems that perplexed him was the distribution of species across the globe. Why did such similar animals live on continents separated by vast oceans? Why do we find marsupials in both Australia and South America, but not in Africa or Asia? The answer lies in Pangea. Many of the similarities we see between the species of different modern continents reflect common ancestors that lived when those continents were joined in the supercontinent. As Pangea fragmented, these ancestral species separated along with the continents, evolving independently for millions of years, but preserving the signatures of their common heritage. Fossils tell us this story with extraordinary clarity. Lystrosaurus, that pig-sized herbivorous reptile we mentioned earlier, is found in what is now South Africa, India, China, Russia, and Antarctica. In our modern world, it would be impossible for a single terrestrial species to have such a wide distribution. But in Pangea, Lystrosaurus simply inhabited a continuous range of suitable habitat that stretched across what are now separate continents. Similarly, the reptile Mesosaurus is found only in Brazil and South Africa, on opposite sides of the Atlantic Ocean. Mesosaurus was a freshwater animal that could not have crossed salt oceans, but when it lived, there was no ocean between those regions. It lived in the fresh water that stretched across what is now the South Atlantic, when that region was part of Pangea's continental interior, and plants tell us equally fascinating stories. The fern Glossopteris is found in fossils from Antarctica, Australia, India, South Africa, and South America. This fern could not have dispersed its spores across oceans, but it did not need to when those continents were joined in Pangea's southern hemisphere. Even modern biodiversity patterns bear the echoes of Pangea. South America has an extraordinarily high biodiversity, partly because it spent a long time as a continental island after separating from Africa, but before connecting with North America. This isolation allowed unique species to evolve that now contribute to the continent's biological richness. Australia maintains its unique fauna of marsupials because it separated from the other continents before placental mammals could colonize it widely. The marsupials that were present when Australia separated evolved in isolation, creating the distinctive fauna we see today. But Pangea's echoes are not limited to terrestrial life. They also fundamentally shape the modern oceans. The Atlantic Ocean that formed from Pangea's fragmentation is chemically different from the Pacific Ocean that existed during the time of Pangea as parts of Panthalassa. The Atlantic is younger, warmer, and saltier than the Pacific, reflecting its different origin and shorter evolutionary history. Modern oceanic currents also bear the fingerprints of Pangea's fragmentation. The Gulf Stream, which keeps Western Europe warm, exists because the Atlantic Ocean opened in a specific way that allows tropical water to flow northward along the east coast of North America. If Pangea had fragmented differently, this current might not exist, and Europe would be much colder. The global thermohaline circulation that distributes heat around the planet and regulates the world's climate is intimately linked to the configuration of oceans and continents we inherited from Pangea's fragmentation. The patterns of sinking and rising ocean water masses are determined by the geography of ocean basins that formed when Pangea separated. Even the modern climate bears the echoes of the lost supercontinent. Global wind patterns, precipitation distribution, and the location of deserts and tropical rainforests are all influenced by the configuration of continents and oceans that resulted from Pangea's fragmentation. The Asian monsoon, which brings vital rains to billions of people, exists in its current form because the Himalayas rose when India collided with Asia after its journey from Pangea. Without that collision, without those mountains, Asia's climatic patterns would be completely different. And the natural resources we extract from the Earth also reflect the history of Pangea. Many mineral deposits formed during the intense tectonic processes that created and then fragmented the supercontinent. The diamonds of South Africa and those of Canada formed in similar conditions because those regions experienced related geological processes when they were part of the same supercontinent. The coal deposits that fueled the Industrial Revolution formed largely during the humid periods that followed certain volcanic episodes during the time of Pangea. The oil we find in the Gulf of Mexico and the North Sea formed in sedimentary basins that developed during the initial stages of Pangea's fragmentation. Even the soils on which modern agriculture depends bear the signatures of Pangea. The fertile soils of the Great Plains of North America developed in part from eroded sediments of the mountains that formed during Pangea's assembly. The rich volcanic soils that sustain agriculture in many parts of the world are derived from the massive eruptions that marked the end of the Pangean era. But perhaps the deepest echoes of Pangea are not in geology or biology, but in the lessons it teaches us about the nature of change and impermanence. Pangea reminds us that nothing on our planet is truly permanent. The continents we consider fixed and stable are actually temporary travelers, constantly moving across the planet's surface on timescales that defy human perception. The oceans we consider eternal characteristics of the Earth open and close in cycles that last hundreds of millions of years. The current geographical configuration of our planet, with its familiar continents separated by recognizable oceans, is only a momentary snapshot in a much longer history of continental gathering and separation. In the distant future, the continents will gather again to form another supercontinent, and the cycle will begin once more. Geologists have already named this future supercontinent Pangea Ultima or Amasia, depending on exactly how the tectonic plates move over the next 250 million years. Australia will collide with Asia. Africa will approach Europe. North and South America might separate or remain joined. The details are uncertain, but the general pattern is inevitable. And when that future supercontinent forms, it will develop its own superdeserts, its own supermountain ranges, its own planetary ecosystems, its own extreme climates. It will be a world as different from ours as Pangea was, a world that will require future species to develop adaptations that we cannot imagine for landscapes that defy our current comprehension. In this cosmic context, our modern world of separated continents is just a moment between supercontinents, a transitional phase in the perpetual cycle of gathering and fragmentation that has characterized our planet for billions of years and will continue for billions of years more. But this moment is our moment. This specific geographical configuration, with its particular oceans and unique continents, has created the conditions that allowed our species to evolve and our civilization to flourish. The echoes of Pangea that reverberate through our modern world are not just scientific curiosities, they are the foundations upon which our entire existence is built. Every time you look at a world map, you are seeing the consequences of forces that operated hundreds of millions of years ago. Every time you experience the climate of your region, you feel the effects of processes that began when Pangea fragmented. Every time you contemplate the diversity of life on our planet, you observe the results of the continental separation that divided Pangea's planetary ecosystems into today's regional ecosystems. And if this exploration through deep time has filled you with awe at the magnificence of planetary change, I invite you to continue this journey of discovery with us here at Dato Terra, because there are so many more stories to tell about our extraordinary planet, so many mysteries to explore about the forces that have shaped our world and continue to shape it today. Subscribe to join us as we uncover more secrets of deep time, as we explore more lost worlds, as we contemplate more scales of change that humble our perspective, but which paradoxically help us to more deeply appreciate the fleeting and precious beauty of the present moment we inhabit. Because in the end, understanding Pangea and its fragmentation helps us to understand something fundamental about the nature of existence itself, that everything changes, that nothing stays the same forever, but that in that impermanence we find both the humility and the wonder that make our place in the cosmos worth contemplating. Good night, and may your dreams be filled with impossible landscapes and timescales that stretch beyond imagination, reminding us that we inhabit a planet that is far more extraordinary and dynamic than we normally dare to imagine.